and this is our work, Efficient Training of Retrieval Models Using Negative Cache. This work is with my collaborators, Sashank Reddy, Riichi Guo, and Sanjeev Kumar. In this work, we study dual encoders and training dual encoder models. In dual encoders, the goal is to learn a model that can match queries to documents. The query data can be a question, or it could be a string used to search a database. The document data could be actual documents, but can also be passages that contain the answer to questions or images in a database. Query data gets embedded by the query network, and document data gets embedded by the document network. We score queries and documents by the dot product or the cosine similarity between these embeddings. We want to have a high score between positive pairs, which is, say, a question and a passage that contains the answer to a question, and a low score between negative pairs, a passage, say, that has no relation to the question. So we can train these networks by scoring the query with a known positive document and a set of randomly sampled negative documents. We'll take the score of the positive pair and the scores of all the negative pairs, and we can feed it into a softmax cross-entropy loss. We'll train the networks to maximize the score of the positive pair while making the score of the negative pairs as small as possible. As we sample more negatives, we often see better statistical performance. However, if we sample too many negatives, we can hit computational limits, such as the amount of memory we have in our accelerator. So in this work, our main idea is to use embeddings from previous iterations to improve training. So what we'll do is we can use embeddings from previous iterations, and this will allow us to increase the number of negatives without increasing the number of calls to the document network. So here we have 9 negatives. However, on this iteration, only 3 of them are fed into the document network. Now to train with a negative cache, let's first take a look at the softmax cross-entropy loss function. We can write the gradient of the loss in the following way. Where we sample an element from this softmax distribution, we get the score of the sampled element, and we compare this score with the score of the positive element, and we take the gradient of the difference. We'll use our cache to approximately sample from the softmax distribution. So we'll consider the following training procedure. We start by calculating the query embedding and the positive document embedding. We'll also have our cache containing the data and embeddings from previous iterations. We'll use the query embedding to search the cache. We'll see that the appropriate way to search the cache is with a perturbed maximum inner product search. We'll find some element and we'll feed that into the document network to get an updated document embedding. We need to feed this through the network again in order to calculate the gradient using backpropagation. Now we'll take the query embedding, the positive document embedding, and the sampled negative embedding, and we'll compute a gradient and update the model parameters. Now we want to efficiently sample from the distribution of the softmax of the scores. To do that efficiently, we'll use the gumbel trick. And how this works is we'll perturb each score by gumbel random noise, and we'll take the maximum perturbed score. This is efficient on accelerators, as calculating the score by dot product is efficient, as well as finding the maximum is efficient. Now we need to update the cache, because note that the embeddings are not changing as the model changes, and so they can become out of sync with their corresponding data. What we'll do is we'll take new negative elements and we'll feed them into the cache with updated embeddings in order to prevent staleness. So we'll have, again, our cache with document data and document embeddings. We'll take some randomly sampled negative embeddings and we'll feed them through the documents. These will just be sort of randomly sampled documents from our data set. Now note that there's no backwards pass needed here because they're just used to update the cache. So this is memory and computationally efficient. Now I'll find the oldest negatives in the data set and we'll add these new negatives. This prevents the maximum number of iterations that an embedding is in the cache from becoming too large. So we're able to theoretically analyze our training procedure. So we have the following convergence result. Let's assume that the query and document encoder satisfy the following properties. We'll assume that both the encoders are order 1 Lipschitz. We'll assume that they're both order 1 smooth. We'll we'll assume that the embedding norms outputted by the encoders are bounded by a constant, and we'll assume that the norms of the gradients of the score functions are bounded by a constant as well. Now, for an appropriately chosen learning rate, we achieve the following first-order convergence bound. So we see that averaged over all the iterations t, the norm of the embedding in expectation, the norm of the loss in expectation, is bounded by 1 over square root number of iterations t, plus 1 over the cache size squared, plus 1 over t times the cache size over the number of updates per step, the number of new elements added to the cache each iteration squared. Let's take a closer look at this inequality. So this first term, 1 over square root t, the number of iterations, this is inherent to SGD, so we do not expect to do better than this. The second term is the error due to the sampling cache. We're not working with the entire database of documents, we just have a sample of it. So this error is due to that. And this third term is the error due to the staleness of the cache elements, the fact that the model is changing, but the cache embeddings are staying the same, that they no longer exactly correspond to what they should based on their data. So now looking at this inequality, we see that we only need the cache size to be t to the 1/4, number of iterations to the 1/4, and we only need to do a constant number of updates per step, that only a constant number of elements need to be added to the cache every step. And if we have these, then we achieve the same asymptotic convergence of stochastic gradient descent. We compare our approach with ANCE, which is a related approach that uses embeddings from previous iterations to improve negative sampling. So in ANCE, they store all of the elements in the data set in the cache, while we saw only a sample of negative embeddings. They search their embeddings using the top K score, while we use perturbed maximum inner product search. They use an approximate nearest neighbor method to search their set of embeddings, which requires an ANN index on CPU. We store all of our embeddings on an accelerator, so we do not require an ANN index. They need to periodically refresh the index due to staleness, which can be an expensive procedure. We do experiments with our method, and we compare it to other related approaches. So the goal in both of our experiments is to match questions to passages that contain the answer. We use BERT-base for both the query and document encoder. In the MS-Marco/TREC dataset, there's 380,000 training example pairs, and there's 8.8 million passages in the dataset. In the natural question dataset, there's 57,000 example pairs in training, and there's 20 million passages in the dataset. We first compare with sampled softmax cross entropy with 256 negatives. We see that even though there's only 256 negatives, this uses actually 87 gigabytes of memory, which is out of memory for the accelerator we consider. Now, if we look at the negative cache with 2 million negatives, this actually requires only 38 gigabytes, so it's much more memory efficient than sample softmax cross entropy. Additionally, it's able to achieve steps per second of 2 compared to the estimated value of 1.4 for sample softmax cross entropy. Now we also see that if we have the full data set in our cache of 8.8 million negatives, this would be 90 gigs of memory, which would actually be out of memory. Now we look at the statistical performance. We see that using the negative cache compares favorably with sample softmax cross entropy. We also compare with several state-of-the-art methods for training dual encoders. We see that the negative cache with 2 million negatives compares favorably with ANCE, as well as DPR, dense passive retrieval, which uses random negatives plus BM25 hard negatives generated by the BM25 method, and also Rocket QA, which is the step 1 of Rocket QA, which uses sample softmax cross entropy with 512 negatives. On the natural question data set, we see that we receive the same statistical performance as dense passage retrieval. However, we do not need the NLP-specific BM25 negatives. Our approach is more generic. And also, we do not need to use the full data set for hard negative mining. Additionally, note that we use less negatives than ANCE. We use only 2 million negatives, while ANCE uses 20 million negatives. Now to summarize, we see that searching the negative cache of embeddings with perturbed maximum inner product search can estimate gradients for the softmax cross entropy loss. We are able to theoretically analyze convergence rates of training with the negative cache, and we see that for reasonably small caches and a small number of updates per step, we can achieve the same asymptotic convergence as SGD. And we also experimentally show that training with the negative cache can compare favorably with state-of-the-art methods. Thank you for listening.